think I did it twice. I'm doing two of these things. Okay. This is I'm jumping around. I'll be jumping around a lot between the various things that are the files that are on the server. So I don't think you have them all here. So you gotta kind of keep track of the number. This is file number 20 on the server. And this is just the last little slide I wanted to show you. We're talking about short-range ordering in liquids. This is a qualitative thing. I'll show you this. This is your magnesium bismuth liquid solution. This is pretty close to the experimental. And in the magnesium bismuth liquid solution, the excess Gibbs energy is negative. This is negative going up here. Excess Gibbs energy is negative, and it's very sharp peak around about 33%. Of course, this is indicative of short-range ordering, because you'll have the enthalpy of mixing, if it's short-range order, has a sharp negative V shape, and the entropy of mixing has this kind of M shape, with this being the 33%. So this is indicative of ordering around the Mg2Bi composition. The sharp. No, I don't want to change the color scheme. Keep the current stuff for this stuff. Okay, so the GX, this is negative. So the sharp negative point here, even negative point here, are reflected in a negative, two straight lines more or less, in a negative peak for GXS. You already know this. And the fact that it's around Mg2Bi would indicate that that's the short range order maximum. So you could treat this, if you wanted to, by an associate model of Mg2Bi molecules. But I would prefer, of course, the quasi-chemical model with the coordination number of bismuth twice that of magnesium. Okay, so this means that magnesium and bismuth tend to order in the liquid at 33%, with every magnesium surrounded by Z bismuth, and every bismuth surrounded by 2 Z magnesium. Now the partial properties, the GXS of magnesium, and this is the GXS of bismuth. The two partial properties are, of course, the intercept and the tangent. You draw a tangent to this curve, and the two intercepts will give you the partial properties. So you can see the partial property of magnesium, which is the intercept over on this side, will remain, if you just imagine rotating a tangent around this, it remains close to 0 and then suddenly becomes very negative. So the GXS of magnesium has that kind of titration thing, which is the, okay, its tangent intercept here stays very straight, almost 0, and then suddenly becomes very negative, and then again more or less constant as you go to the other side. And GXS of bismuth has the same approximate shape. So if you're looking at partial properties, a partial property that has this kind of shape is also indicative of short-range ordering, and the point where it changes abruptly is around the short-range ordering composition. There is another property which you'll see in some of the literature, especially some of the older literature, called the excess stability function. There doesn't seem to be any particular symbol for it, but call it the excess stability function. And this is defined as the second derivative of GXS with respect to, it doesn't matter, xb squared or xa squared, comes up the same thing. It's the second derivative, and this really even just magnifies it even more. Like the second derivative of this, the second derivative is the rate of change of the slope, so you can see that that goes up really rapidly. If you were to, in this system, magnesium bismuth, if you were to plot the second derivative, you would get a curve that sort of looks like this. This would be negative up here. This is your excess stability function, negative. So your excess stability function goes up, and then all of a sudden there's a very, okay, which indicates stability around, this would be 33%. So the peak in the excess stability function kind of magnifies this rapid change of slope, and that indicates that this is a composition of excess stability, or kind of indicates you've got some sort of ordering, short-range ordering around that point. And this is, you'll see this used in the literature, often the excess stability function. The excess stability function, you can play with it. For example, calculate the excess stability function of a regular solution. If you set Gxs to be omega xAxb, work that out yourself, calculate the second derivative, and you'll find the excess stability function is a constant. That is, in the regular solution, there's no excess stability. If omega is positive, then the excess stability function will be negative, but constant. If omega is negative, the excess stability function will be, sorry, this is positive. It's stability. So if, sorry, this stability means if you have a negative Gxs like this that's changing, that gives you a positive stability function. This is the more stable. Obviously, the second derivative there is positive. Okay, so a positive excess stability function indicates stability relative to, say, a regular solution. So if omega was negative, you would get a positive excess stability, but it would be constant across the whole system. If you have a peak, it indicates that the system is becoming more pointed, or in other words, the regular solution parabola doesn't give you a peak in the excess stability. So the excess stability is a way of magnifying the short-range order tendency, and you'll see that sometimes. Now here's something interesting. These are from some good measurements, excess stability in the potassium tellurium alloys. Maybe I should make this a little smaller. These are potassium, even smaller, potassium tellurium liquid. This is always liquid, I'm talking about liquid. This is potassium at the left and tellurium at the right. You always, by the way, expect this. I mean, magnesium and bismuth are, if you have two materials, this is quite electropositive at the left of the periodic table, and this is electronegative at the right. That's when you expect to have short-range ordering. You know, I mean, the positive ions tend to surround themselves by negative. It becomes kind of semi-ionic, if you like. It's still an alloy, but I mean, the magnesium has a tendency to lose charges to the bismuth, and so it's electropositive and electronegative elements tend to form strong bonds. So potassium and tellurium, potassium is very metallic, tellurium is basically a semi-metal intermetallic, and this is the excess stability function. And isn't it interesting, you have two peaks in the excess stability function, and possibly even a tendency towards a third peak here. And this would indicate that you have in fact two compositions of short-range ordering. This is completely miscible. You go from potassium to tellurium, but around 50% potassium, you have a very strong short-range ordering, with potassium and tellurium being second nearest neighbors in a 1-to-1 ratio. But you also have a quite strong peak at about 12.5%, indicating some sort of short-range ordering with about 8 times as many potassiums around a tellurium. I'm not quite sure what that would be, but it's some type of an ordering, or you can imagine kind of like a, locally, it almost looks like a solid crystal structure locally for a few atoms around a central atom. And you may even have another tendency here around 33%. So this indicates as you move across the liquid, it's like moving across a series of intermetallic phases. If you go across a solid diagram, you can have a number of intermetallic solutions. This would be like KTE8, this would be KTE2, KTE, and so on. There'd be stoichiometric compounds with different structures. You can imagine as you go across the liquid is completely miscible, but you tend to have local structures that kind of look like a series of intermetallics as you're going across. You see this quite frequently in systems. Here is sodium and potassium tellurium. Now you might expect potassium is more electropositive than sodium, and so again in potassium you have a higher tendency towards stability. In other words, there's more ordering in potassium because it's more electropositive. The sodium is less electropositive than potassium, but you still have the same type of peak here and the same sort of tendency here, although it's more rounded. As I said, the excess stability magnifies this. The excess stability are places where the second derivative is high, where the first derivative changes rapidly of the Gxs curve. So you can imagine really what it's looking at is something like this, you see. There's a change here at 12% and a change here at 50%, the second derivative. So every time you get like a fairly rapid change of slope of the Gxs function, Okay, if you just plot G excess, you don't really see it, but when you plot the second derivative, then it becomes quite evident. You need pretty accurate experimental data to do this. Okay, so again, it indicates you got kind of a series of not just one composition of preferred short-range ordering, but you can have several. This is manifested. Now, the short-range ordering often, but not always, corresponds to the idea that the short-range ordering maximum applies to the is it the same composition as the solid compounds isn't necessarily true. Actually, there are no data in the liquid over on this side because it's too high a liquid, but here's 50%, so there is a compound at 50% here, but it's not the strongest. The strongest compound is at Na2Te, but you actually don't see that here because we don't have the data on that side because you can't measure the liquid up very high. But when you have a very strong compound, it's almost like this. In other words, in the sodium tellurium system, if we could measure at higher temperatures, I'm certain that if you went out here to 67%, you'd find a very strong peak, indicating there really are three. This is the strongest. Na2Te is the strongest. 50-50 is less strong, and this is even less strong. Okay, and what you get, of course, when you get the very strong peak, this is almost like a compound, Na2Te. The liquid is almost like a liquid compound. So you've got a very, very steep liquid that's coming down here. And on this side, the compound doesn't really want to mix with sodium, so you've almost got a miscibility gap. The 50-50 compound, although it's quite strong in the liquid, doesn't actually come up very strong in the solid, and this one at 12.5%, there's no solid at all that corresponds to that liquid. So there's not necessarily a one-to-one correspondence. I'm not sure what this... Actually, I think this is the excess stability function at higher temperatures for that system. Yeah, it has been measured at higher temperatures. So there's your 33% roughly, or 75% or whatever, and 50. Or maybe that's the system. I'm not sure. Anyway, here's another system again. It doesn't really matter. The point I'm trying to make is that you do find a number of these systems going from an electropositive to electronegative atom in which you have more, you have a tendency to order at more than one composition. Now, how do you treat this? The quasi-chemical model only treats it, or can only treat one composition of ordering, AB. You have ZA over ZB. Your complexing model, of course, makes it easy. You could have MG, it could have AB complexes, A2B complexes, A7B, you can have all sorts of complexes. That would make it quite easy to fit with a complexing model, except, I don't believe the complexing model is reality. But there are ways of treating this with the quasi-chemical model, which I won't go into in detail. We have used it. You would actually have, if you have A, B, and then you have different minima, you have different kinds of B. You could imagine here you have A, here you have B1, here you have B2. B1 coordinates with A in a 1-to-1 ratio. ZB1 over ZA is equal to, say, 1. You have B2, have a ZB2 over ZA equals 3 or whatever, gives you a minimum here. And then it means that pure B is somewhere, the actual system goes along here, so in pure B you actually have a mixture of the two coordinations and so on. So you actually treat it as a ternary system, A, B1, and B2 with the quasi-chemical model, and then pure B is some mixture of B1 and B2 depending on their relative G0, so you don't have to worry about that, but we've used that in the sodium fluoride, aluminum fluoride in model cryolite. In the cryolite system between NAF and ALF3 you have at least two compositions of maximum ordering for ratio of 4, ratio of 5, not a ratio of 6, which you might expect. And these are treated by talking about sort of different kinds of aluminum fluoride. I won't go into the detail, but there are ways of extending the quasi-chemical model to actually treat more than one minimum. And there are a number of these. Now these systems are these kind of alloys. If they're metallic, are often called ionic alloys. And the reason being that when you have an electropositive and electronegative ion, the tendency is to have an electron transfer. And probably the most flagrant one of this is the cesium gold system. If you consider the cesium gold phase diagram, it looks like this. There's actually a solid compound, cesium gold. And as you go across the liquid, up here the liquid is completely miscible. in the cesium gold phase diagram. Cesium and gold are both metallic, of course. They have quite different electronegativity. Cesium is the most electropositive material there is, apart from maybe francium, which that's hard to come by. And if across the liquid you were to plot the excess stability function, you would find it went boom like this with a very strong peak at 50% cesium. So at 50% cesium gold, in the liquid state, you pretty well have cesium ions surrounded by gold ions, cesium ions surrounded by gold ions, like the cesium chloride structure. Okay, cesium gold, cesium gold, cesium gold. And what's happened is the cesium has given its electrons over to the gold to make it basically an ionic material, even though the two ends over here are metallic. And it's completely miscible. Now this is interesting because if you look at the 50-50 liquid at exactly 50-50, it has no electronic, it's not an electronic conductor, it's an ionic conductor. It's translucent, not a metal, it's light blue I believe, and you can see through it. It has an ionic the conductivity goes way, way down. Electronic conductivity goes down to 0, becomes an ionic solution, basically. And the density also goes through some huge peak because here you have a less close packed structure than the cesium gold. So basically, if you look at band theory, here you have your conduction band, and here you have your, so all the electrons are down here, and they're connected with the gold. And then as you start to add a little bit of extra gold, as you get away from 50-50, you add 0.5% of extra gold, you're forming a gold, let's put it this way, go a little bit the other way, you add a little bit of, so if you're at 50-50, you have cesium ions and gold ions. As you go a little bit to the left, you're adding additional cesium. The cesium goes in to form an ion, and the electron that it gives up goes up here into the conduction band, and essentially becomes a free electron, and you get an N-type semiconductor. As you go to the other side, you add the gold, a little bit of extra gold atoms, they become gold ions, and they take an electron away from the valence band down here, and you get a hole type P-type semiconductor. And as you go even further, then of course it becomes metallic. Okay, so you go across, you go from metallic conduction to N-type semiconduction to ionic conduction to P-type semiconduction back to metallic conduction. The heat of mixing is very, very negative. These other materials such as potassium, tellurium aren't that flagrant, so as you go across here it still remains an electronic conductor, but the electronic conduction goes way down around the compositions of the maximum short-range ordering because you're getting a lot of electron localization and you don't have many free electrons left as you do in the metal. So these are kind of interesting materials. People talked about them as ionic liquid alloys. So, I just want to look at that qualitatively. One last thing, this I believe is, how do you explain this? This is the excess heat capacity. I do believe, okay, this is potassium tellurium. And this is where your peak is at 50%. Okay, so this is liquid potassium tellurium, and this is the excess heat capacity, the deviation from the Neumann-Knopp additivity rule. So you have an excess heat capacity which is maximum around the ordering composition. And you generally, this is another thing, the excess heat capacity has this peak, and the peak is at the same point as you have the ordering. Okay, so why do you get this excess heat capacity peak? This is another evidence for the, remember what does excess heat capacity look like if it's the slope of the enthalpy curve? So if we were to plot the enthalpy, this is the enthalpy at this 50-50 composition, the enthalpy would kind of look like this. The enthalpy comes up, and then around the 50-50 there's a tendency here to increase. Basically what this means is as you heat the at 50-50 you have ordering, so you have the ordering. But as you heat the material, as you heat the ordered material, it tends to become disordered. Okay, because the entropy becomes more important. As you go to very high temperature, everything becomes ideal. Okay, so the ordering decreases as you go to higher temperature. And of course the ordering, you have ordering because you have a negative heat. The energy of forming these bonds, the delta H is negative to form the bonds. As you decrease the ordering, or the heat of mixing, the heat of mixing is negative like this, but as you increase the temperature, the heat of mixing becomes less negative. Okay, because the entropy, you have fewer AB bonds, less ordering, so you don't get as much negative entropy, so you absorb heat. Okay, so as you increase the temperature, the ordering decreases. The ordering is associated with the negative enthalpy to form these strong nearest neighbor AB bonds. As you increase the temperature and decrease the ordering, this negative heat is lost, so it takes heat. You have to absorb heat to break up the AB bonds, just like breaking up a compound. When you heat a compound, it takes heat to associate. Okay, so this is your excess heat capacity, and it's positive everywhere, because everywhere you're breaking, there's ordering everywhere across the entire system, but the ordering is maximum at 50%, so that's where you get the maximum excess heat capacity. Okay, any questions about this? So if you have strongly ordered material, and remember the quasi-chemical model, if you use a Bragg-Williams model, we often assume the heat of mixing and the excess entropy of mixing are constant, independent of temperature. But the quasi-chemical model takes into account the fact that the heat of mixing decreases at higher temperature. Quasi-chemical model takes into account the interaction between the heat and the entropy, and at higher temperature the entropy term wins, as always. So the heat, with quasi-chemical model, the heat, even though your quasi-chemical parameters are constant, the heat of mixing is not constant and will become less negative as you go up in temperature, because you're breaking up the disorder is decreasing. So the quasi-chemical model does give you naturally an excess heat capacity, even if you have constant parameters. But if you have constant parameters in the Bragg-Williams model, if delta H and SXS are constant, then the parameters are constant and delta H is in fact constant, because delta H is just a constant times the polynomial of the mole fractions. So the quasi-chemical model does at least partially take this sort of thing into account and predict it. Questions about this one? Okay, that's all I want to say about long-range order and short-range order. Now I want to start talking about long-range order. And long-range order basically means sublattices. So long-range order, sublattices are the same thing. The sort of philosophical difference between long-range order and short-range order is sort of interesting. I mean, you can imagine even like a lattice, let's say a one-dimensional lattice, but the same thing applies in 3 dimensions. You could have a central atom here, and then you can have short-range order. Short-range order would mean that if you have a central atom, it's more likely to have a B. If it's completely the probability of if this is a central A, the probability of a B here in a completely disordered system would be the mole fraction of B. If it is greater than B, or less than B, then you have short-range order. Okay, but of course the short-range order is short-range. It disappears very quickly as you go across the lattice. Even if the short-range order is very high, supposing that the probability, saying you have a system, say A 0.5, B 0.5, and the probability of B being here is 99%. So the fact that I have an A here, there's 99% probability of finding a B here, and 99% probability of finding an A here, or even 99.9%. So the system, for all intents and purposes, is AB, AB, AB. But of course, this disorder adds up, and after you get out to 10 or 20 atoms, it's becoming basically disordered. Okay, so if you have an A here and you're considering an atom that's 25 distances away, what's the probability that it's a B? It's the mole fraction of B. Okay, there's no long-range order. That's short-range order. Now, in a long-range order, you basically have 2 sublattices. You have a sublattice for A, and you have another sublattice for B. A and B. I mean, you know, for example, the cesium chloride structure, for example, you have the cesium chloride unit cell, you have cesiums on the corners, and that's one sublattice. And then in the center of the cell you have your chlorine, which is the other sublattice. And these are distinct sublattices going on for huge numbers of atomic distances. Okay, so this is quite distinct from short range order. This is a long range ordering. Now you can have then, this is an A sublattice and this is the B sublattice. This is the A sublattice and the B sublattice. This means that if I go on 10 million lattice sites from here, the probability that this is a B is, well, okay. If it's completely long range ordered, every other site is a B. Okay, I'm talking about a 50-50, A one half, B one half composition. Okay, this is the A sublattice, which is normally occupied by A, and this is the B sublattice, which is normally occupied by B. The corner sites are normally occupied by the cesiums, and the center sites are occupied by the chlorines. Now you don't have to have complete long-range order. There's a possibility that every now and then you can have substitutional disorder. A chlorine could go to the center, or a cesium could go to the corner atom. This would mean this is A, B, and occasionally there might be a B on an A site. Substitutional disorder, or occasionally there might be an A on a B site. A substitutional disorder. And this could even be quite high. The substitutional disorder could be 90%. But still, if you go an even number of lattice sites, you go 2, 4, 6, 8, 1 million, 1 million and 2, the probability is still greater than 50% that that's going to be occupied by a B. You get my point? So it's fundamentally totally different. So you can have almost complete disorder, but still it's long range ordered. Even though the system isn't very ordered, it's still long range. It's 2 sublattices. You go on 1 million lattice sites because that's an even number. The chances are greater than 50-50 that it's going to be occupied. So here you can have a lattice that at first glance, this is long range order, but with a very high substitutional disorder. So when you look at it, it looks almost disordered, A, B, B, A, B, B. And yet the probability, no matter how far you go, is still greater than 50% that there's long range order. So here you have a lattice that looks disordered, but at long distances, even at long distances, it's ordered. On the other hand, as I said, the short range order, you could have 99.9% short range order, A, B, A, B, A, B, so it looks perfectly ordered, but at long distances it's completely disordered. There's your fundamental difference. And long range order is always associated with sublattices. And you can have a system with both long range order and short range order. You can have a long range ordered lattice, and then you can have a short range order possibility as well on top of the whole thing. Okay, let us now look at, I'm going to go back to this, you better write these down, this is, because you don't have these names here, this is handout number 1. The reason this is number 1 is before I wrote that chapter that we use at the beginning of the course, I used this chapter which I wrote 20 years ago. Okay, so this is number 1. And let's go to page 50. Now the whole theory of sublattices, this can cause a little confusion, but I'm going to present the thing this way because this is how it was actually developed. The whole theory of sublattice, okay, sublattices clearly cannot apply to a liquid. Okay, a liquid cannot have long range order. Obviously. Okay, but some liquids are have so much short range order that for all intents and purposes, for modeling purposes, we can treat them as having 2 sublattices. It's so much simpler to treat them as having 2 sublattices. Because remember, in all the models we've been talking about, the quasi-chemical model and the regular solution model, the parameters are only dealing with first nearest neighbor, second nearest neighbor forces. We're not talking about long range forces. So if a system has locally virtually 2 sublattices, for all intents and purposes, it's easier to treat it long distance. So let's say we take sodium chloride, liquid. Sodium chloride solid, no question, it has 2 sublattices, an cation lattice and an anion lattice. Okay, and sodium chloride solid is fine. Sodium chloride liquid, however, to all intents and purposes, can be treated by the same model. You can have positive ions and negative ions. And although we know that as you go further and further away from the central ion, you have some possibility of substitutional disorder. It's so small. The probability that a chlorine is going to be on a sodium site and a sodium on a chlorine site is extremely small. Okay, you got to get a long way away before you start to find disorder. So we can, since we're only dealing with nearest neighbor forces, in modeling we can treat liquid ionic salts as essentially being formed of two sublattices, even though in reality we know this isn't the case. Okay, and this is historically the way this was developed. In the 60s, 1960s, there was a huge interest in molten salt chemistry, mainly because there was a lot of funding from the Americans and the Norwegians to build nuclear reactors which used molten salt coolants. And it was just also theoretically really interesting back then, and a whole lot of the whole sublattice theory really developed around molten salt chemistry. Also, there's a lot more measurements on molten salts than there are in solid salts. They tend to be more miscible. It was easier to do the measurements and so on. Okay, so I'm introducing long-range order sublattice using a liquid which officially really doesn't have long-range order. But now to treat this, okay, you could treat sodium chloride and alkali mixtures as a one sublattice model with an extraordinarily amount of short-range order. So you could treat these really as sodium and chlorine mixed randomly on the lattice sites, okay, and then you would have sodium plus chlorine gives you 2 sodium chloride, and you could treat it like a quasi-chemical model with one sublattice with a very, very negative constant here. But that would be ridiculous because you're almost entirely at this composition, and this would be so negative that you're always just, you'd solve the quasi-chemical equation and you'd find out that you always have sodium chlorine, it would just complicate matters. Okay, so we're treating it. However, solid salts we can treat as, in solid salts it is really 2 sublattices. Liquid salts, we treat them as if there were 2 sublattices. Now, sodium, here we have the system, sodium, potassium, chlorine, fluorine, and this is the phase diagram. In the liquid state, the 4 salts are completely miscible at all compositions. Okay, in the liquid and the solid state they're not. In the liquid state there are four salts can mix. Now what we write this generally then, this way we write sodium, potassium, brackets, chlorine, fluorine, to indicate that sodium, potassium go on one sublattice, and the chlorine and fluorine go on the other sublattice. Okay, so on the positive lattice sites here, you can put sodium and potassium form a solution, one solution on the cation sites, and the chlorine and fluorine ions form another solution on the negative ion sites. Okay, so this is your, basically all your sublattice models are based upon that. You have a solution, sometimes a random mixture, on each sublattice. Each sublattice forms its own sort of solution. Although you can get some crossovers sometimes, as we'll talk about later. Okay, now we talked before about the how you represent this. This is a liquidus projection. These are isotherms of the liquidus, and I showed this earlier that this is how you treat these sort of things, where this ratio here, the horizontal axis is the chlorine-fluorine ratio. So the horizontal axis would be the number of moles of chlorine over chlorine plus fluorine, or it's the anionic fraction. And the vertical axis is sodium over sodium plus potassium. So the x-axis here is the mole fraction of chlorine on the negative ion lattice, and the vertical axis is the mole fraction of sodium on the positive lattice. And although you have 4 salts, you only need 2 composition variables. So it is thermodynamically, it's a ternary system. The number of components is equal to 3, because the number of sodium plus potassium must always equal the number of fluorine plus chlorine. Okay, so this is called a reciprocal system. In this case, a reciprocal salt system. This is actually called a reciprocal ternary system. A reciprocal system contains at least 2 species on one sublattice and at least 2 species on the other sublattice. Okay, so at least 2 species and at least 2 species here, that's a reciprocal system. If it's exactly 2 and 2, then it's a reciprocal ternary system. We could, of course, add lithium here, we could add bromine here, it would still be reciprocal systems, they would then be reciprocal quaternary, quinary systems and so on. But a reciprocal system always has 2 sublattices with at least 2 on each sublattice. Okay, and so this is your projection of the liquidus, and you see the liquidus surface coming down here. Okay. This is the experimental diagram up here. Sorry, this was the experimental diagram down here. At the bottom is the experimental diagram. This is a diagram predicted by the model I'll be talking about. Okay, so if you look at this handout or file number 1, you go to page 62, you will find a bunch of equations in which we introduce the sublattice model, starting at page 62, ionic solutions. Okay, but this uses a somewhat older notation. This was written in 1991, I think, and since then there's a more modern notation, which also is the modern notation that's used by other people, CalFAD people and so on. So I'm going to talk about the same thing here. If you want to read this is okay. Starting at 110.1.2 on page 62 and reading on for 2 or 3 pages. Okay, but up to page 64, it's not long. But there is a more modern notation, which is in here on 29A, which I called equation 119 to 122. So 29A is the more recent notation for the sublattice model for this particular system: sodium, potassium, fluorine, chlorine. Just other notation, this is a modern, sometimes we write it this way: sodium, potassium, chlorine, fluorine, with a couple of slashes in here. I've seen it written that way. I've seen it written as sodium, potassium, semicolon, chlorine, fluorine. There's different ways, but this tends to be the way that people do it now. And you probably want to put the charts on here. So indicates 2 sublattices. Now in this particular model, we're assuming that there is no crossover, that all sodium and potassium only go on these lattice sites, and chlorine and fluorine only go on these lattice sites. For the moment, anyway. Okay, so here we have a little yi, which is called the site fraction in modern notation. People tend to use small I. And this is basically the fraction of the sites on a sublattice. This is the mole fraction on that particular sublattice. In the file 1, I used big X here, like mole fraction, but this tends to be more modern. Okay, so the site fraction of sodium is simply the number of sodiums over the number of sodiums plus potassium. So it's sodium over sodium plus potassium. The fraction of these sites that are occupied by sodium, and this is 1 minus site fraction of potassium. Okay, since we're assuming that only sodium and potassium can go on these sites. And the site fraction of chlorine is the chlorine over, which is 1 minus the site fraction of fluorine. We now have, just for definition, this is called the delta G of the exchange reaction, and this is the difference of the Gibbs energies, G naughts, of the pure liquid salts. So G naught is the Gibbs energy of pure sodium fluoride, G naught KCl is the Gibbs energy of pure liquid KCl, and so on. And this is the delta G for the exchange reaction. And the exchange reaction is simply this plus this gives you this plus this. So the exchange reaction would be, the exchange reaction then is sodium chloride plus KF gives you NaF plus KCl. That's the delta G of that reaction is the delta G of the exchange reaction. So it's delta G of G naught sodium fluoride plus G naught KCl minus G naught sodium chloride minus G naught KF. And so this is the delta G of the exchange reaction. Okay, so this can be positive or negative if the exchange reaction, if delta G exchange is negative, then NaF and KCl are called the stable pair. And NaCl and KF are called the unstable pair. Okay, if delta G exchange is positive, then the reaction tends this way, and NaCl and KF will be called the stable pair. If NaF and KCl are the stable pair, then this is called the stable diagonal, and this is called the unstable diagonal. Stable pair are at the 2 ends of the stable diagonal. Okay, so that's your exchange Gibbs energy, which is among the pure liquid at the corners. Of course, if this was a solid solution, this would be the Gibbs of the solid solution. These would be the Gibbs energies of the pure solids at the corner. Same thing. It doesn't happen to be liquid. This could also be the solid solution. Okay, so now we write the Gibbs energy of the liquid. What do we write for the Gibbs energy of the liquid? Well, you know, in the Gibbs energy expression, you have a G naught term, then you have a ideal mixing term, then you have your excess terms. Okay, so if you had a simple system AB, you would have G is XA G naught A plus XB G naught B plus RT XA log XA plus XB log XB plus a GXS term and so on. Okay, how do we do it here in the two sublattice system? Let's start with the configurational entropy. Now in the configurational entropy we have two sublattices. So we have sodium and potassium mixing on one sublattice and we have chlorine and fluorine mixing on the other sublattice. Okay, so we have these are two ideal mixing terms. This is your RT, Y sodium log Y sodium. This is for your ideals. You're assuming an ideal solution of sodium and potassium on their sublattice, and here's an ideal solution of fluorine and fluorine on their sublattice. Okay, so these are just this is per mole of total. This is G per mole of salt, which means there's 1 mole of cations and there's 1 mole of anions. Okay, so KF, this would be 1 mole, KF, 1 mole of KCl. But this is G, where you got 1 mole of cations and 1 mole of anions. Let's give it a simple example first, where the cations and anions all have the same charge. It doesn't have. When you get to something like Mg2, then you've got additional problems, but let's keep it here. So there's your ideal mixing term. Okay, so now how do we replace the G naught term? Okay, we can't just go mole fraction of sodium chloride. Okay, what does it? The mole fraction of sodium chloride actually is even, we go back for a second, I call this a ternary system. If you were going to make up a mixture here, you had 4 bottles of salt in your laboratory, you had a bottle of each one of these salts in your laboratory, you would only need 3 of them to make up any composition. In other words, let's draw a diagonal through here. Anything in this triangle on the right hand side could be made using these 3 bottles. Anything that's underneath this triangle could be made using these 3 bottles. You never need all 4 salts to make your material, so you really only have ternary system. Okay, let's do it this way. G, this is the expression we tend to use here. Now let's go across a binary solution, NaF, NaCl. So along this solution here, you're mixing sodium fluoride and sodium chloride. Okay, along that binary solution, the Y of sodium equals 1 and Y of potassium equals 0. Okay, so let's go along that. Okay, let's go along the NaF, NaCl binary. Okay, we're on the top line here, the NaF, NaCl binary. Along that Y binary, Y sodium equals 1, Y potassium equals 0, and if we substitute that back into here, we get G equals Y chlorine times G naught sodium chloride plus Y fluorine times G naught sodium chloride, which is what you want. Okay. It gives energy if you mix sodium fluoride and sodium chloride is the Y chlorine. Now along that binary, Y chlorine, in that binary, Y chlorine equals the mole fraction of sodium chloride. And Y fluorine equals the mole fraction of sodium fluoride in that binary system. The one lattice is completely occupied by sodium. If you're going from NaF to NaCl, all the positive sites are occupied by sodium. You're only mixing fluorine and chlorine on the negative sites. The site fraction of chlorine is the mole fraction of sodium chloride in the binary system. The site fraction of fluorine is the mole fraction of sodium chloride. And the Gibbs energy, as you go across here, goes from sodium fluoride to sodium chloride, just like it does in any binary system. Okay. How should we then weight then if you went across here? In the KF-KCl system, you would get the same thing, Y chlorine plus KCl plus Y fluorine. How are you going to vary in between them? Well, let's multiply it by the fraction of sodium-potassium ratio. Okay, so this is G naught sodium chloride times this fraction of sodium times this fraction of chlorine. Or let's put it another way, what is the probability? If this is kind of some sort of mechanical mixture, how are we going to do it? Well, so G naught sodium chloride, what is the probability that this is a sodium and this is a chlorine? Well, it's Y sodium times Y chlorine. Okay, so this is the probability, this is the number of sodium chloride nearest neighbors. This is the number of potassium fluorine nearest neighbors, sodium fluoride, KCl nearest neighbors. So this seems another logical way of weighting it. We take, if we're going to do the first term, we take the probability of sodium chloride nearest neighbors and multiply that by G naught sodium chloride, the KF nearest neighbors times G naught KF, and so on. And you can verify yourself that Y sodium, Y chlorine plus YK, YF plus F equals 1. Okay, this is Y sodium times chlorine plus fluorine. This is Y potassium times chlorine plus fluorine. So altogether is, if you add these up, you get Y sodium plus Y potassium times Y chlorine plus Y fluorine, so 1 times 1. Okay, so this is the probability of a sodium chloride nearest neighbor multiplied by G naught sodium chloride. So this is a most logical way of doing it. And it's not the only way of doing it, but it works. It's sort of part of the model if you really like it. This is how they do it in all the sublattice models. Now I see some people looking puzzled, so you want me to go through that again? No? This reduces then to this binary thing on all 4 sides. Along this side, this equation, this first line here would be mole fraction of sodium chloride times G naught sodium fluoride plus mole fraction of Kf times G naught Kf. Same thing on all 4 binaries. In between it varies linearly. Okay, you get the right G naught expression in this binary. You get the right G naught expression in this binary, and between the 2 binaries it varies linearly. Okay, so there's your G naught expression. But we have to have this model, by the way. The model we do has to reduce to the binary model in each binary, which it does. This first term reduces to the binary expression in any binary. This term here reduces to the binary expression in any binary too. In the NaF-NaCl system, the first term here is 0 because all the cation sites are occupied by sodium. Only the second term, and so on. So this reduces to all the binaries, exactly. Okay, so far so good. Now, in the binary systems, we also have excess terms. Each binary system has an excess term. Okay, so how do we treat that? And this then is treated like this. Okay, first of all, let's look at the, this is the sublattice model, the standard way, compound energy formalism. This is what's used by CalFed, SGTE, thermocalc, everybody. This is the 2 sublattice equivalent of the polynomial model. Random mixing. This is the Bragg-Williams model in 2 sublattices, what we're doing. So it has to reduce to the Bragg-Williams model in every binary system. Okay, so let's take, say, the sodium chloride, let's say sodium chloride, potassium chloride system. Take the binary sodium chloride, potassium chloride system over here. And in the sodium chloride, potassium chloride system, we have the GXS is equal to alpha NaCl, KCl times X sodium chloride times X potassium chloride. Okay, or the alpha, if this is a regular solution model, the alpha is n naught Z over 2 times 2 epsilon AB minus epsilon AA. It's the nearest neighbor bond energies. Okay, it's a regular. We're treating the sodium chloride, potassium chloride binary system as a regular solution. But what do we mean by these bond energies? Now, these aren't the nearest neighbor bonds, because the nearest neighbor bonds are the same in the pure material as in the. Okay, these are the second nearest neighbor bonds. These are. Okay, the alpha here is n naught Z over 2. Times 2 times the energy of a sodium chlorine potassium bond minus the energy of a sodium chlorine sodium bond minus the energy of a potassium chlorine potassium bond. So AB is sodium potassium with the chlorine in between. AA is sodium sodium bond, like you get in pure sodium chloride. BB, these are second nearest bond energies because the first nearest neighbor bond energies don't change. Let's say I take sodium chloride and potassium chloride. The number of sodium chlorine nearest neighbors is going to be the mole fraction of sodium chloride. The number of moles of potassium chlorine nearest neighbors is going to be the mole fraction of KCl. And this doesn't change when you mix them. If I take pure sodium and potassium chloride, if I take a mole of sodium chloride and a mole of potassium chloride and mix them, the number of sodium chlorine bonds stays the same. Every sodium is still going to be surrounded by a chlorine in the mixture. Every potassium is still going to be surrounded by a chlorine in the mixture. Okay, so when you form a solution, if you mix NaCl and KCl, the number of first nearest neighbor bonds doesn't change. Every sodium still has only got chlorine nearest neighbors, and the same thing with potassium. What changes is the number of second nearest neighbors. Okay, you have the number of sodium-potassium bonds will change, the number of sodium-sodium and potassium-potassium bonds. Basically, you just forget the positive ion lattice, just the negative ion lattice. Just forget the chlorine lattice. Look only at the sodium-potassium sublattice, and it's a one sublattice model. The chlorine sublattice just goes along for the ride, and the sodium and potassium are mixing randomly on the cation lattice as a regular solution. And the bond energies we're talking about then are the second nearest neighbor bonds. So you can treat then this is called a common ion system, NaCl, KCl. And although this common ion system is really a sublattice model, since one sublattice is occupied entirely by chlorine, you can just forget it. And you apply a one sublattice model just like any binary system. So the sodium chloride, potassium chloride system, you can apply everything we've talked about up till now for a one sublattice model. It's just exactly the same thing. The second sublattice is just dropped. Or if you take this equation here, let's just do it this way then. Let's now take this. Okay, so let me just finish up for that and then I'll show you, prove it. Okay, so here's your NaCl, KCl. This is your Y sodium. Okay, so this then GXS, then in the binary system NaCl, KCl should be the alpha for the NaCl, KCl. And the mole fraction of sodium chloride in that binary system is the site fraction of sodium, is the same thing as the mole fraction of sodium chloride if the other lattice is completely occupied by chlorine. And the mole fraction of KCl becomes the mole fraction of potassium. Okay, so that is how you would write the binary interaction, the second nearest neighbor interaction in that binary system. Now, how is that going to be weighted as you move across, as you start to add fluorine? Okay, well this is the energy of a sodium-potassium bond when they're separated by chlorines. This is a sodium-sodium bond separated by a chlorine. Potassium-potassium bond separated by a chlorine. The number of each of those bonds will decrease as you decrease the number of chlorines. Okay, so we multiply it by something that's hidden by this stupid thing over here under there. Okay, here's your binary term here. In the binary system, when Y chlorine equals 1, when there's only chlorine on the lattice, and we're going to multiply that term by Y chlorine to show how the second nearest neighbor terms decrease as you add fluorine. And on the other side, then, on the other side over here, on the NaF-KF system, so we multiply by Y chlorine. So as Y chlorine's 1 here, and it decreases here. This is the other side, NaF-KF. So this is your binary term on this binary over here, and we multiply that by Y fluorine, which is 1 here, decreasing to 0 over here. Or in other words, the binary term varies linearly. These last two terms here, this is the binary term on this side, this is the binary term on this side, second nearest neighbor binary term, and the binary terms in the ternary just vary linearly between the two sides. These are second nearest neighbor sodium-potassium bonds, but on one side they're sodium-potassium separated by fluorine, which will have a different energy than sodium-potassium separated by chlorine, so we just vary them linearly from one side to the other. All right? Okay, so these are your binary second nearest neighbor terms. This is your second nearest neighbor terms in the sodium chloride KCl binary, weighted by the number of fluorines. This is your sodium-potassium second nearest neighbor bonds in the sodium chloride KF binary, weighted by your number of fluorines. Then we have second nearest interaction between the negative ions, between the ions. Why have I lost? All right, so these will be the first term here then. These are the terms, these are the second nearest neighbor terms along here between the positive ions. These are the second nearest neighbor terms between the negative ions. So if we're down in this binary here where you have only potassium, this is the second nearest neighbor interactions between fluorine and chlorine when the other sublattice is occupied only by potassium, and up here is the same thing when the other sublattice is occupied only by sodium, and so we vary linearly between the two. Yes. Okay, so now we have the G naught terms. which are basically the lattice energy. This is the lattice energy for a sodium chlorine bond. This is the lattice energy when all the bonds are sodium chlorine bonds. And we multiply that by the probability of finding a sodium chlorine bond. This is the lattice energy when you have KF, potassium only KF bonds, and we multiply that by the lattice energy by the probability that a nearest neighbor bond is KF. Then we have the ideal mixing of the ions on one site and the ions on the other site. Then we have the second nearest neighbor interaction terms, which are the regular solution type terms from the binary systems. So we have the cation interactions varying from one side to the other as the anion varies from fluorine to chlorine, and then we have the anion-anion interactions as you vary this way. And now just to continue to prove a point, let's just take this then for the, okay, let's take this equation. I've still dropped the last term here. Okay, but this is the sublattice model, two sublattices, Bragg-Williams mixing. By the way, these alphas, of course, can vary with composition. This alpha will vary with composition along here. Doesn't have to be constant, it can vary with composition. Okay, let's take this equation and let's apply it to the sodium chloride KCl binary. And what I'm trying to show now is that this equation will reduce exactly to the binary one sublattice model for NaCl, KCl. Okay, so what I'm going to say YCl equals 0, Y fluorine equals, YCl equals 1, Y fluorine equals 0. Okay, so you have only chlorine on the one sublattice. And now Y of sodium is going to equal the overall mole fraction of sodium chloride, and Y of potassium is going to equal the overall mole fraction of KCl. Make those substitutions into that equation, and you will find that G equals X sodium chloride, G naught sodium chloride, plus X KCl, G naught KCl, minus RT, X sodium chloride, ln X sodium chloride, plus X KCl, ln X KCl, plus alpha NaCl KCl, times X NaCl, X KCl. Making these substitutions up here into this equation, you get this equation, which is a binary mixture of A and B. Okay. Sodium chloride is A, potassium chloride is B, XA G naught A plus XB G naught B minus RT XA log X sigma. So, okay, you've forgotten the chlorine sublattice, and this is just mixing sodium and potassium on the cation sublattice. And the interpretation of this alpha term here is the second nearest neighbor interaction energy. Remember, the energy of the second nearest neighbor sodium-potassium bond is going to be different if there's a fluorine in between as if there's a chlorine in between. Okay, so it reduces exactly to the binary systems on all four sides, which we want it to do. So if you have data for all four binary systems, if you've optimized all four binary systems, and you have values for the G naughts as well, you can estimate the reciprocal salt ternary liquid using this equation. And of course, the slags, the molten oxides that you're using, are treated like molten salts, and this is exactly what we're doing. In the molten oxides, the one sublattice is occupied by oxygen. Okay, so you're really treating, say, CaOMgO is being treated as you're forgetting the oxygen, you're just treating the calcium and magnesium mixing on the sublattice. Okay. So even though, your oxide solution has two sublattices, so this could be more than one thing. You could have a mixture of sodium chloride, potassium chloride, lithium chloride, copper chloride, iron chloride. Okay, it's still a one sublattice model. All the cations mix in one sublattice, all the anions mix in the other, but it's only one anion, so you just forget that, it's a one sublattice model. It's obvious, I think, how you would extend this to more components. If you had other components, you would just, if you added lithium, then you would have to have Y lithium, Y chlorine times G naught of lithium chloride plus Y lithium, Y fluorine plus G naught lithium fluoride, plus you'd have to add a Y lithium here, or you'd have to just add additional terms for each pair. So this can easily be extended to more than just the ternary system. You can add more cations and more anions. Then you have a term here for each pair. Okay, so each pair would have a term here. All the cations have this term, all the anions have this term, and each pair has a form like this. Okay, let's go back. Unfortunately, if you just use this here, you don't get the greatest estimation of what goes on in the ternary system. Okay, here's something then. If you have optimized all four binary systems, so you've looked at each binary system and you've optimized it to get the best phase diagram, okay. Then can you predict the reciprocal system from this equation? And the answer is no, because you've got to have the delta G of exchange. Remember, you don't need the actual G naughts here, okay, to optimize a binary diagram. You only need the delta G of mixing in the liquid to optimize a binary liquid. You need the delta G in the binary system, NaCl, KCl. I don't need the G naught of NaCl and the G naught of KCl separately. All I need is the delta G naught of mixing in order to get an expression for the Gibbs energy of the liquid phase. But here, I needed the actual delta G of exchange. So I need the Gibbs energies of the pure materials. And this turns out to actually be the most important thing. And this information, another way of looking at it, is not given by the binary systems. Okay, the binary systems only show if I mix sodium fluoride and potassium fluoride, they just show how sodium mixes with potassium. But the number of if I mix any binary system, the first nearest neighbors stay the same. If I mix NaF and KF, all the first nearest neighbors are still fluorine with fluorine. If I mix NaCl and KCl, the first nearest neighbors don't change. Same thing here, if I mix KF and KCl, the first nearest neighbors, anion and cations, don't change. But when I make the reciprocal solution, the first nearest neighbors are changing. If I mix these salts here to make a composition in the middle, okay, now I'm getting first nearest neighbor changes. First nearest neighbor meaning positive, negative ions, sodium, fluorine, potassium, fluorine. The number of first nearest neighbors is changing. If I mix two binary salts like this along the edges, the first nearest neighbors don't change. It's only the second nearest neighbors change. And the first nearest neighbor energy, of course, is much stronger than the second nearest neighbor energy. Okay. So if I mixing any binary salt, if I just take a binary phase diagram, binary enthalpies of mixing, I do the optimization, the only information I'm getting from my binary optimizations is what happens when second nearest neighbors change. I'm not getting any information on what happens when you change the number of first nearest neighbors, which is the most important term. And that's tied up with these. So just your binary optimizations don't allow you to make this approximation. The most important terms in this whole thing, in this whole model, are these G naught terms here. So let's go back to page 50 back here in number 1. The idea here is to look at the mathematics, but to see what the mathematics means. Okay, let's look at this system. The four binary systems, if you've ever seen them, are almost ideal solutions. The liquid solutions of NaF, each of these binary liquid solutions is almost ideal. These alpha terms are very small. Yet look along here, this is very widely spaced liquidus lines along this diagonal, NaF, KCl. The liquidus lines here are quite widely spaced. Along this diagonal, they're closely spaced. Okay, so you've got quite strong positive deviations along this line. If you were to draw the binary phase diagram along that diagonal, so let's take here, this is going along the diagonal. I'm going from NaF to KCl versus temperature. You're going to get a curve that looks a lot like that, quite This S-shaped curve is strong positive deviations. If you go along the other diagonal, well, you cut different regions here, but the diagonal drops down quite rapidly. This positive deviations is the stable diagonal. So if I go NaCl plus Kf produces KCl plus NaF, the delta G of exchange is negative. The exchange energy is negative. So this is the stable diagonal. Generally in these diagrams you often you see the line drawn here along the stable diagonal. And along the stable diagonal, this is just a very general rule, along the stable diagonal you get positive deviations. Along the unstable diagonal you tend to get negative deviations. And this has nothing to do with the binary systems, which can be very close to ideal. This has everything to do with the delta G exchange. Okay, this is the major feature of all reciprocal diagrams, and I'm not just talking about reciprocal salt, I'm talking about any sublattice model for the solids, compound energy formalism. When you have more than two things on each sublattice, this is the overriding feature of the whole thing. Why do you get positive deviations along the stable diagonal? Would anybody like to explain that to me? Let me show you how bad this is. To do this, I'm going to go to, no. You don't have to, look at this. Look, this is number 29, but you might want to look at 29. You see there's a whole lot of subs. Here's another one. Here's lithium, potassium, fluorine. Look at the positive deviations along that stable diagonal. Very, very flat. There's one temperature, 50 degrees lower. Very, very flat. Stable diagonal shows very positive deviations. Look how steeply their liquidus is going down along the unstable diagonal. Very, very fast. And again, the binaries are not far from ideality. Maybe here, look at this one. Calcium. This is calcium, magnesium, fluorine, chlorine. Positive deviations along this stable diagonal are huge. Very, very flat liquidus coming along here. Always the case along the stable diagonal. Stable diagonal means that this pair, the delta G of exchange, will be negative with this pair here as the product. So that's the stable diagonal. Stable diagonal along here. Sodium, potassium, fluorine. If you want to go to, show you one more. What happens if the delta G exchange becomes positive enough, becomes large enough? If it becomes large enough, you can end up with a miscibility gap. Here's your, up here, this is experimental diagram, this is your lithium, potassium, bromine, fluorine. The stable diagonal is lithium, the stable pair is lithium, fluoride, potassium, bromide. Delta G exchange is negative. And what's happened is if you're going along that diagonal from lithium fluoride to potassium bromide, it actually ends up with two liquids. This is a miscibility gap along here. Two liquids centered along the stable diagonal. So this is also very typical of these molten salt systems, of reciprocal systems, is along the stable diagonal you have a positive deviations, which if the delta G exchange is negative enough, can actually be a miscibility gap, and the tie lines in the miscibility gap are generally centered along the stable diagonal. Okay, so as you go along this phase diagram, it comes down, then you have two liquid region. There's like, imagine there's temperature coming up, there's like a dome up here. Alright, so why do you get that? No, stable diagonal. In this case, the delta G exchange is negative. It's not negative enough to provoke an immiscibility gap, but it's certainly negative enough to give you the strong positive deviation. Okay, this is the stable diagonal. This actually seems paradoxical backwards. If NaF and KCl are the stable pair, if delta G is negative, then you think along the stable pair you might expect to get negative deviation. Stability, negative deviation. Get along the stable pair, that's where you get positive deviation. They don't want to mix. Potassium likes to stay next to chlorine, first nearest neighbors. KCl and NaF nearest neighbor bonds are preferred over KF and NaCl nearest neighbor bonds. Okay, when you mix these, if you mix NaCl and KF, you're forming strong bonds. You're forming KCl and NaF. If you take NaF and KCl and you mix them, if you take KCl and you mix it with NaF, then you're forcing the potassium to be next to some fluorine. You're forcing the sodium to be next to some chlorine it doesn't want to be. So the stable pair want to stay apart. They don't want to mix. Meanwhile, the unstable pair, they want to mix because they're forming the stable nearest neighbor. So this is a first nearest neighbor effect. Okay, and it's totally dependent upon the delta G of exchange. Or in other words, it depends upon the delta G, the difference between the G naughts. The delta G of exchange then is equal to G naught KCl plus G naught NaF minus G naught NaCl minus G naught KF. And this is probably the most important parameter in your entire reciprocal model, because this is what determines this effect here, which is really, really big. The second nearest neighbor effect is really a second thing. And this is, however, is not given by your binary optimizations. This is an independent term. As this delta G exchange gets even bigger, then you get a separation into two liquids. Okay, so that's the most important term. All right, now that then is the reason why you get this. So now I will go through the mathematics of it. Okay, after a 10-minute break. If you understand the mathematics, you can get lost in the mathematics. The reason is potassium wants to stay next to chlorine, sodium wants to stay next to fluorine. If you mix them, you force them to be next to neighbors they don't want to be next to. We don't like to have neighbors that we don't like. Okay.